Okay, so we are now 20 people in the session, and I think we are ready to go. Good morning, everybody, and welcome to this third day of DTIP 2021. So we have a very interesting program today, and we will start with a session on mechanical design. My name is Peter Schneider. I'm with the Fraunhofer Institute for Integrated Circuits in Dresden, Germany, and I'm also the co-chair of the CAD conference. And we can now look forward to very interesting presentations. And our first speaker is Do Young Ha. He received a PhD degree in electrical engineering from KAIST in Korea in 2000. And currently he is an assistant professor of electrical and electronics engineering at the Abdullah Gül University in Turkey. Before joining the Abdullah Gül University, he worked at Louisiana State University, the University of California in Los Angeles, and Electronics and Telecommunication Research Institutes. So I think we are ready to go. We have a pre-recording.
Hello.
And we are looking forward.
The title of my presentation is The Effect of Curved Beam Heights to Harvested Energy in a Balanced COM-Drive Configuration. This is the outline of my presentation. First, I will give the introduction about energy harvesting, energy harvester bandwidth, broadband structures, and then finally spring nonlinearity. Then I will introduce the device structure. Then I will describe the method that was used for the analysis of the device. Finally, I will present the results. Energy harvesting has become an important research topic. It has various applications such as IoTs, wireless sensor networks, and implantable medical devices. Our main research focus is with vibration energy. Some vibration energy sources have specific resonances, such as infrastructure and the factory equipment. Others have random broadband frequency characteristics, which can be described as colored noise, which are from typical environment. Energy harvesters need to have matching frequency characteristics to those of energy sources. For example, if the energy sources have specific resonances, then one can use such a structure with distinct resonant frequencies. On the other hand, if the energy sources have colored noise frequency characteristics, then one should include the broadband structures. There have been different approaches attempted to incorporate broadband structures in energy harvesting devices. In one approach, they used Dolphin oscillators. In this example, there are magnets with the same polarity. Therefore, this structure will try to go away from the center line, and hence this one has multiple stable positions. In another approach, they included a number of harvesters in an array, and these devices have different resonant frequencies, so that overall the device has the broadband frequency characteristics. In another approach, they use multi-degree of freedom structure, which has number of resonant frequencies which are close to one another. Yet another approach utilizes spring nonlinearity, which can be described as Dolphin-Holmes oscillator. Here we have an illustration of a typical mass spring damping system. And this system can be described by this motion equation. When there is a spring nonlinearity, these two terms appear. Even the straight beam can have nonlinearity if it has a boundary condition of clamped condition. And the cubic term appears due to the stretching of the beam on the load. One can also have the quadratic term if the beam is curved like this. As an extra information, the beam can have bistability depending on the beam height. And if the beam height is larger than the critical beam height, then it can have bistability. And this critical beam height is dependent on the beam width. Let me talk more details about the spring coefficients. Apparently, the spring coefficients are the function of the spring dimensions and the material property. What is interesting here is about this beam height. And as you can see, the beam height appears in the linear term and the quadratic term. This is a reason why the spring straight beam also has a cubic term nonlinearity, because it does not include h. Two things happen when h increases. First, the spring coefficients increase. Two, the nonlinearity increases because of the increase in the quadratic term. This is a device structure which follows that developed by Professor Toshioshi's group. It has a balanced comb drive configuration. You can see two combs, fixed comb A and fixed comb B. This is to enhance power harvesting at low acceleration. The comb drives form electrets by having charged dielectric on the surface of the fingers. The main difference from the original device is the curved beams. What is given here is a circuit model of the device. A voltage source model was used for the electrets. Vs represents the surface potential of the electrets. C1 and C2 are area-varying capacitances of the comb drives. RL represent the load resistances of the circuit, and CP models the parasitic capacitances of the device. Now let me talk about the methods used for the analysis. Mainly we use the stochastic differential equations. The first one is the velocity. The second one is a motion equation, which include the external force term. So this one models the random vibration. So Wiener process was used to model the random vibration. And the sigma is the diffusion coefficients that sets the strength of the acceleration. F-elec is the electrostatic force that follows the electric circuit model, which was presented in the previous slide. Fr indicates the restoring force. For the Wiener process, random series was generated from MATLAB, and one signal length was 20 million, determined by the capacity of the machine that was used. It had a time step of 0.1 microsecond. And for more accurate analysis, it was repeated with differently generated signals, and the average was taken. Here is the FFT of average of the generated signals. For example, when there is just one signal, this green curve, then the FFT becomes quite spiky. But as the number of signals increase, the average becomes quite smooth. Quantitatively, we can look at the standard deviation as a function of number of signals. And the standard deviation decreases exponentially according to the number of signals. Eventually, we used 2,000 signals and then took the average of it. Here is an example of signals, not the averaged one, just one signal. The first one is external force. The second one is displacement of the structure, velocity, and an acceleration. This is the charge in one comb drive, and this is a current that was delivered to the load. Here we have point care maps for different conditions. The left-hand side, we have the case of straight beam. On the right-hand side, we have the case of curved beams with a H of 1.5 critical beam height. Top ones are the case of 0.1 g acceleration, which means 0.98 meter per second. And the bottom ones are with a higher acceleration of 0.5 g. When we compare these two, we can see that in the straight beam case, there is more displacement because of lower spring constant. When we compare these two, at lower acceleration, the displacement is around the original stable position. In the higher acceleration case, we can clearly see the snapping between two bistable positions. This is a result of PSD, power spectral density. It shows the electric PSD for various beam heights. And this is a case when the acceleration is at 2g. In the case of straight beam, this black curve, we can see the clear resonant peak and the higher resonance due to the nonlinearity coming from the clamped beam nonlinearity and the electrostatic force. And as the beam height increases, we can see the resonant peak increases because of the strengthening of the spring, and also we can see the broadening of the peak due to the nonlinearity of the spring. Finally, this is a calculated harvested power with different beam heights and load resistances. As well known, there is an optimum load resistance for the maximum power transfer. Also, there is an optimum beam height which varies for different load resistances. For example, in this case, the green curve, for which the load resistance is 0.3 mega ohm, power is a maximum with a straight beam, H is 0. In other cases, from 0.5, actually from 0.4 to upper higher load resistances, the maximum power is achieved at the curved beam. The maximum power does not vary much for the range of 0.5 mega ohm to 0.9 mega ohm. In the case of electrical power, we can see much remarkable power change, maximum power change in the case of mechanical power. Ultimately, we can see that for the case of straight beam, the maximum power achieved was 1.77 milliwatts when the load resistance is 0.5 mega ohm. And with the curved beam, the maximum power achieved was 2.69 milliwatts when the load resistance is 0.6 mega ohm and the beam height is 0.5 HCR. As a summary, colored noise responses of vibration energy harvesters with balanced COM drives and electrets were studied by using stochastic differential equations. Effects of curved beam heights to harvested energy were studied. For a given condition, 52% of power improvement was observed by employing curved beams in comparison to straight beams. This improvement also depends on the condition, such as the vibration acceleration, and further study is needed. Thank you for your attention.
So thank you very much for your very interesting presentation. So we have time for some questions and of course for reactions. And I see two questions. So Etienne, would you start, please?
Yes, hi everyone. Thank you for your talk. So I'm Etienne Puyot from INL in Lyon in France. I have a question regarding the elaboration process of such harvesters. How can you control the height of the curved beam?
In this device, the beam height of the spring is predefined by the lithography, when you make the mask. So it is not. There are two ways to make the curved beams. One is the press from the side, and the second one is by patterning from the mask stage. Okay. So the idea was from the mask stage. Yes.
Okay. Thank you.
Okay. Thank you. So the second question from Paco, please.
Hello. Do you hear me?
Yes.
Thank you for the talk. I was wondering which interface circuit did you use for calculating the output power? Because you need a yes, like you have an electrostatic transducer and you need a circuit interface where you yes, I mean all the diodes, like it was just a rectifier or a Bennett doubler, or which kind of circuit it was the one you did the simulations on?
Oh, when I calculated the electrical power, I just used the voltage and the current that is on the resistor. So in this case, the loading was just a simple resistor.
Okay, so you just put a resistor on your transducer and did the calculation.
Yes.
Okay. Well, thank you.
Okay.
Thank you.
One short question from my side. Do you expect a significant impact of temperature on the behavior of the structure, since you have this clamped beam and thermal expansion could affect the behavior?
Oh, sure, yes. I also expect there should be a thermal influence, but I haven't considered it yet. That's in the future.
Okay.
Thank you for your comments.
Thank you. Thank you. So at the moment, I can't see any further questions.
There is one from Emil.
Oh, right.
Yes.
Thank you.
No.
sorry, Emil.
Yes, I was jumping from the window to the paper, so I'm reading I'm reading the.
Yeah, and I have two screens with a participant, so maybe you were on the wrong side.
So I had a question about the design of the COM drives and so on. So you got harvesting in quite high frequencies, and your device is I see 8 millimeters long, or is it the spring? Which is the size of your device? I missed that in the presentation.
So I didn't elaborate on that during the presentation. It's in the paper. So it's quite big. It's quite big structure, but it's also it has strong spring, and that is why the resonant frequency is around 50, 70 hertz. Yes.
Mm-hmm. And so if you explore the design map, could you? Is it easy to tune this frequency range of the harvesting, or would it be more difficult if you change the stiffness or the size of the device?
Well, I don't think it will be particularly difficult, because the aim is to broaden the bandwidth. So as you saw in one of the slides in the results, so it is quite broad. So I don't think the particular resonant frequency is that important. As long as it's within the low frequency, then it should be fine, in my opinion.
Okay, thank you very much.
Okay.
Thank you.
Thank you. Any further questions? Can't see any further questions, so let's thank our speaker again.
Thank you very much.
And we can go to the next paper, and we can welcome the next presenter, Naga Manikanta Komanaboina, who was right, received the master degree in aerospace engineering from the Kaunas University of Technology, and he is currently pursuing a PhD degree with the University of Trento in Italy. The current research is concerned with the design and development of novel MEMS devices, and research interests in general include MEMS for space applications, 2D materials, characterization, micro and nano devices, and the design and development. And we already published 8 papers in international conferences. And I think it's an online presentation, so we're ready to go. And we can see the presentation, so the floor is yours.
Thank you for the introduction, sir. So as you said, this is Naga Manikanta. So and I would like to thanks to my supervisor, Maria Pantano from the University of Trento, and Alvisa Bogolny from the FPK. So investigation of the 2D materials under the strain is necessary to understand their behavior as they maintain very good properties like physical and chemical, so which might lead novel applications. There are different types of 2D materials have been popular recent days, like graphene, hexagonal, boron, molybdenum, tungsten, and etc. So each material has their different advantages, like graphene. So it has a monolayer thick and it can accommodate the large strain, around 25%. It has a high stiffness, and it is 200 times stronger than steel and lightweight. Moreover, it is high conductivity. So this kind of material can be used in the semiconductor industry, for the flexible electronics, energy, biomedical industries, and aerospace and mechanical industries. So recently, the guys from MIT have developed a graphene skin wing, and they found there are a lot of advantage on it. There are some other research going on rockets and satellites for the solar sails and other structures. So the main aim of our project is design and simulation of a novel MEMS devices for the mechanical and strain engineering characterization of 2D nanomaterials. So the requirement of our device is having enough stiffness to control the displacement and the temperature management in the structure, and enough sensitivity to read the displacement at the sample. So we are going to use SOI MEMS technology, which have a different advantages like a miniaturization testing platform, which can easily put into STEM for inspection. And we have VRAD silicon oxide thickness is around 1 micrometer, and it operates in low temperatures. Also, just occupy tiny space and required low power. So the fabrication limitation that we consider in this project is the minimum feature size 4 micrometer, and the minimum gap is 2 micrometer, and the device layer thickness is 25 micrometer. So this is our schematic view of our device. As you see here, there are 3 different stages. So in the beginning, we just consider a thermal actuator connected with the sample to perform the tensile test. And we understand that there is a need of heatsink beam to reduce the temperature at the sample. So we use the heatsink beams. So due to these heatsink beams, we lost displacement delivered to the sample. To maintain the displacement, required displacement at the sample, we use the symmetric structure. And this is our final stage of our device, 2 thermal actuators connected with the sample. And this is amplification mechanism to amplify the displacement to the capacitive readout. And for the simulation, we use the ANSYS 2019 version. And stage 1, as you see here, there is a good displacement without any heatsink beams, and the temperature is 195 degrees Celsius. And the second stage, the symmetric structure, there is a good displacement at the comb structure. As you see here, this amplification mechanism connected with the combs. Due to the sake of easier simulation, we just considered few of them, combs. As you see here, there is a problem with long shuttle, and moreover, we are not able to measure the displacement near to the sample. So that's why we designed one more design, configuration 2. As you see here in the configuration 2 model 1, we use the C-type structure to increase the displacement as well as reduce the shuttle and make it stiffness. And now we are able to read the nearest possible to the sample, and this gap we left for the gold plate for other purpose in future. So as you see here, the comb drives, there is a problem here due to the high number of combs. So the structure may be unstable and break down during the fabrication. So that's why we introduced some kind of bars, supporting bars with anchor points and side settle to increase the stability and maintain the good stiffness, not to break during the fabrication. This is the total temperature we observed in simulation model 2. So as you see in this graph, so temperature and displacement linearly increases with voltage at the sample that we consider. So this is the boundary condition that we consider in multiphysics simulations. This is a thermoelectric condition. These all right parts are mechanically fixed. This is the total stress that we observe. So here you can see how our device is going to work in the real case. So this is our final device that we model, 2 capacitive readouts with 2 thermal actuator. So there is a small beams, V-shaped beams with small hinges to magnify the displacement, and there is a heatsink beams and amplification beams. So there are H holes for the fabrication purpose we used to release the HF wafer. And these amplification beams we selected based on multiple simulations, and we observed that the displacement is inversely proportional to the angle, and we selected the best one. For CAD model, we use a SolidWorks 2020 version, and device stiffness. The total device stiffness is 40,053 Newton per meter, and the sample stiffness that we considered in the simulation is around 835 Newton per meter. The sensitivity, the theoretical sensitivity is 5.2 femtofarad per nanometer. So finally, we are able to reduce the temperature to 80 degrees Celsius, and the displacement is reduced to 0.4 micrometer at the sample location when you operate with 3 volts. The configuration 1 gives the displacement amplification factor 19. So this factor can be calculated as maximum displacement over displacement delivered to the amplification beams, and the stress 73 megapascal was observed. And in the configuration 2, model 1 moves with factor 22, but with smaller resulting stiffness, and stress will remain the same as the configuration 1. In model 2, it moves factor 19 with high resulting stiffness. The maximum stress is 71 megapascal observed. The maximum temperature, all these 3 models, is around 132 degrees Celsius. So the magnification ratio for the final device that we selected in this is about 22. So this magnification ratio calculated as final displacement means the total displacement at the amplification mechanism over displacement delivered to the sample. So there is no squeeze filling damping effect in our case, since it is operating quasi-static in vacuum condition, and the residual stress will be neglected in SYE vapors. The future work will be concerned with the microfabrication of this proposed device by using SYE vapors and deep reactive energy. Thank you.
Thank you very much. And try to clap hands. Okay, thank you very much for your presentation. And we have time for some questions. So are there any questions for the?
Yes, I have a question.
But I can't see your hand. So. Okay.
So I've seen your design. I just a question about final fabrication. So your project is to have some device to test the mechanical properties and so on of graphene or 2D materials. So I suppose when your drawings, when you put the sample in the middle of your tips, this is where the sample will go. And so how? So at the moment you design the actuator, but how do you imagine you will put your 3 samples in there in the tip of your device?
Actually, we are going to use only one sample on it, and with the help of the gold for adhesion purpose. So unfortunately, the technology we cannot tell now. Maybe in future we are going to reveal the technology of this gripping of 2D material.
Okay.
Yeah.
Thank you.
Thank you.
Okay, thank you. Any further questions? I can't see further questions, so let's thank the speaker again. Thank you very much for your presentation. And we can go to our next paper. The presenter is Teferi Sitotar Yale, with a background in mechanical engineering, and Teferi is currently in the second year of a PhD at the Department of Civil and Environmental and Mechanical Engineering at the University of Trento. And the current research focus is on design and application of MEMS for micro-manipulation. And this will be the topic of the talk. So the finite element analysis of an terminally actuated microgripper. So we're looking forward to your presentation.
Okay, thank you, sir, for the introduction. I'm Teferi, and my supervisors are Maria Antonov from University of Toronto and Aloise Bagolini from Fantasini Bruno Kessler. Today I'm going to present the design and finite element analysis of an electrothermal actuated microgripper for biomedical applications. First, I will try to give some introductions about the microgripper. Microgripper is one of the MEMS device which is aimed for the micro manipulation of objects. Mainly, it has three applications. The first one is pick and place of biological samples to the testing devices. The second one is for biological material characterization, and the third one is for the microassembly of micro components. So far, there are a lot of microgrippers developed, and the main gap is its actuation and sensing systems are not compliant with the liquid environment. So our motivation is to design and fabricate a novel MEMS microgripper for biomedical applications, especially in a liquid environment. So before we are going to the design, we had two design considerations. The first one is the tip moving range of 50 micrometer for each gripper arm, and the minimum position sensor sensitivity of 100 femtofarad per micrometer. Next, I will try to describe about the components of the design structure. The first one is the microgripper. As you see here, it is the central part. This microgripper is constructed from the conjugate surface flexure hinges, as you see here. I and J are the revolute conjugate surfaces, and these conjugate surfaces are joined by a flexible thin curved beam. And these conjugate surface flexure hinges are developed by Nicolas Pupil-Ferré, and he got an international patent in 2009. And the second part is the electrothermal actuator. Actually, when we compare with the other actuation types, it has two advantages. The first one is it provides a large force under a relatively low voltage, and also it is robust against the moisture formation. But it has one drawback. It induces high temperature during operation. So to control this high temperature, as you see here, we added heat-sink beams in cascade with the electrothermal actuator. These heat-sink beams will dissipate the heat to the surrounding fluid or the device frame. So by using these heat-sink beams, we could reduce the temperature around the tweezers by 105 degrees Celsius. And the other component is the capacitive readout for the safety of the gripper as well as for the safety of the grasped objects. These capacitive readouts are important. Next, I will try to show you about the working principles of this conjugate surface flexure hinges. First, the actuation force which will drive from the actuator develops a vertical force Fa on the link L1.
So when this link moves in the upward direction, the conjugate surface I1 rotates in the clockwise direction around its center of rotation with one end of the thin curved beam. Then the other end of the curved beam develops a reaction force Fr to resist this rotation. So because of this reaction force, this inclined link, as you see, it will move in the upward direction. And then the conjugate surface J2 will rotate in the counterclockwise direction around its center of rotation. In the end, this rotation will develop a gripping force, as you see, at the tip of the tweezer, and at the end, the gripping of the biological sample will be possible. To check the performance of the micro gripper, we have done a finite element analysis by using ANSYS. Actually, it is a coupled thermal electric mechanical analysis. This is the boundary conditions to get the intended displacement of 50 micrometers on each tweezer. As you see here in the thermal electric, we have two boundary conditions. The first one is our actuation voltage is 3.8 volt. And the other one is, as you see, the one which is described by the red color, these are the anchor points. On the anchor points, the temperature is ambient. And when we see the mechanical or static structural boundary conditions, the three anchor points are mechanically fixed. This one is the intended total deformation. As you see here at the tip of the tweezer, the maximum deformation is 50. I can show you a video how the micro gripper works. And to say our design is safe or not, we have to check the temperature profile as well as the stress field. As we see here, when we see the temperature profile, the maximum temperature is 707 around the shuttle of the electrothermal actuator. When we compare this maximum temperature to the melting point of the material, that is silicon, it is lower, so it is an acceptable value. And also when we see the equivalent stress, as you see here, the maximum equivalent stress is 330 around the thin curved beam regions. And when we compare this value with the yield strength of silicon, it is below that. So based on the temperature profile and the stress field, we can say that our design is safe. And in the end, we have done a sensitivity analysis of the capacity readout. As you know, the total sensitivity is the ratio of the total capacitance to the output displacement or the displacement of the tweezers. When we see the total capacitance, as you see from the diagram, we have two components. The first one is from the tip of the movable finger to the root of the fixed combs. The second one is in between the fixed and the movable fingers. So the total capacitance is the sum of CF and CG. This one is the relation to find the total capacitance. It is described in terms of the geometrical parameters of the capacitive readout. So by using the both formulas, the total sensitivity of the capacitive position sensor is 100 to 10 farad per micrometer. This is above the intended sensitivity of the sensitivity of the capacitive readout. So it is an acceptable range. So to conclude, in the design, the fabrication limitations and technological constraints are considered. These are, for example, the device thickness of 25 micrometer, minimum feature size of 6 micrometer, and minimum gap size of 2 micrometer. And the other point is the achieved performance of the final design. Tip total displacement of each user is 50 micrometer. That means 100 micrometer in total. To get this displacement, the actuation voltage is 3.8 volt. And the maximum sensitivity of the position sensor is 100 to 10 farad per micrometer, and the device size is 4.4 by 0.5 by 0.025 millimeter. And our future plans is about the microfabrication, validation, and application of the micro gripper. Thank you for your attention. If you have any questions or comments, welcome.
So thank you very much for your presentation. So you were very fast, so we are significantly ahead of time, so we have plenty of time for questions. And are there any questions from the audience? I can't. Abe, yes, please. Yeah, you're on mute. Unmute.
Thank you. I hope that everybody hears me now.
Yeah, perfect.
Yeah, thank you very much. Thank you for the presentation. Really interesting device. Can you comment on the robustness of this device? You know, in terms of applied force. You know, when it does the gripping, how fragile or how robust is it? Have you done any analysis of it?
Actually, in the future, so far we didn't do any force analysis, but in the future we are gonna do force analysis because we are gonna grasp sensitive biological samples. So because of this, we have to do some force analysis in the future. Yeah.
Okay. So, but is that part of your design specs? I didn't see this in your design specs, you know, for this device. And I think it might be an important design spec in terms of sizing the different parts of the device.
Yeah. Actually, I included it in the full paper.
Okay.
Here, because of the time limitation, I didn't include here.
Okay. Thank you very much.
Okay, thank you. Emil, you have a question?
Yes. I'm very impressed by the model. It's really a very, very big work to put all these devices in the simulation software. So I have a couple of questions about that. So I suppose it took a long time to enter that to model that and to carry out these simulations. And can you comment a little bit on that? Let's say how big is the model? How much time it costs to, for example, for one structural simulation or for one thermal? I suppose what you showed was transient simulation when you showed the movement of the displacement of the tip. So just can you say a few words about that?
Yeah, actually, as you see here, we have simulated only that part of the micro gripper to save the simulation time. Because if you see the overall structure, it is a kind of symmetrical. So to save the simulation time, what we did is I simulated only the half part of the micro gripper. So in this way, we can save the simulation time.
But how much time does it cost? For example, you pinch the simulate button and you go home and you wait for 1 week, or
No. Just it will take like 10 minutes or 15 minutes because we didn't include the capacity readouts. If you include the capacity readouts, it will take more time.
And do you have in mind the number of elements you have in your simulation?
You mean the components?
The small squares are I suppose you meshed it by
yes, tetrahedral. The tetrahedral, yeah. Tetrahedral, yeah.
And do you have in mind how many tetrahedra you have in your simulation?
I didn't exactly remember, but it is around 2,000 or more, maybe, because we have used the fine mesh.
Yeah, I suppose.
Yeah.
Because but because your results are surprisingly nice for tetrahedra, but it's very nice. And another question, but I suppose it's a more difficult question because you are not running into fabrication, but you said that you have a thickness of 25 microns. So I suppose you'll be using SOI wafers if you target silicon, and then 25 microns thick to etch with 2 microns gap is quite demanding. I'm having it in mind, but I think it's quite, it's a little bit risky. But yes, it's very ambitious. It's a very ambitious device.
Yeah, actually it is risky, but the main point is to increase the sensitivity of the capacitive readout, we have to reduce the gaps between the fingers of the fixed combs and the movable. Like if you reduce the gap, we will get more sensitivity. That's why we reduced it to 2 micrometers to achieve the intended sensitivity.
Mm-hmm. Okay, thank you very much.
Okay, thank you. And just one question from my side. So you have these heat sink beams in the structure. Could you comment on the design considerations for these heat sink beams? So they are additional elements, and maybe they have an impact on the movement of the structure. So maybe you have specific design measures taken to prevent this impact or to minimize this impact.
Yeah, actually, the main importance of these heat sink beams is, for example, this tweezer has a direct contact to the biological samples. So the temperature around the tweezer must be ambient. For example, if the temperature is above the ambient, it's going to damage the biological sample. That's why we added heat sink beams here. So we have used like the width of the heat sink beams is 10 micrometer, and the gap is also 10 micrometer. It became somehow stiff, but by using this magnification conjugate surface plate gear hinges, we could get the intended displacement.
Okay, okay, thank you. Then let's go to our next paper. Our presenter is Jose Francisco Ambia Campos. He was born in Mexico in 1995. He received a bachelor in mechatronics from the Universidad La Salle, and afterwards a master in nanoscale engineering from INSA in Lyon, and he did his master thesis on MEMS packaging at Université de Sherbrooke. And now he's preparing the PhD thesis on energy harvesting for biomedical implants at the Center of Nanoscience and Nanotechnologies at the University Paris-Saclay. And the paper is on energy harvesting for implants, as we heard before. And we're looking forward to your presentation. And we have again a pre-recording, I guess. Yeah, right. Okay, let's go.
Hello, everyone. My name is Francisco Ambia. I'm doing a PhD on Université Paris-Saclay. And today I'm going to talk about the design we've been working on of an electrostatic energy harvester that we intend to use for biomedical implants. So we want to use our device to power leadless pacemakers. So these kind of devices are very thin because they go with a probe through the artery. They reach the heart and they get implanted inside the heart cavity here. So this is very comfortable for the patient because this way there's no invasive surgery. But the problem is that as we have a very thin device, a very small device, we have less room for batteries. So we need to look for supplementary sources of energy, and we want to use the heart movement to transform it into electricity and power the device. So here's our device. It's made on a silicon on glass wafer to avoid parasitic capacitances. And we are going to add a tungsten mass in order to bring down the resonant frequency of the system in order to match the spectrum of the heartbeat. So once the supplementary mass is on the system, we're going to add a second device that will, instead of moving in this direction, in the vertical direction, it will move in the perpendicular direction, in the horizontal direction, in order to use these two movements of the heart. So once the two devices are together, we're going to put them into their packaging that is a cavity of 5 millimeters of diameter and 2 centimeters length. So this is the device that is going to go inside the vein and get implanted in the heart cavity. So all the elements that we use to design our springs are doubly clamped beams, as the one you see here. So these beams, we allow them to keep their length in order to avoid nonlinear stretching terms. That's why you see it moves a little bit to the left. It follows this parabolic trajectory in order to keep its length constant. From now on, we are going to use a color notation. In black, you will see elements that are fixed. In red, there are elements that can move and they can deform. And in blue, there are elements that they don't deform, but they move. So the first geometry that we're going to study is the opposing beams geometry. So if you try to move the device in this direction, in the vertical direction, you will find a very low restoring force. So it will move very easily in this direction. Whereas if you try to move it in the perpendicular direction, horizontal direction, it will be very difficult. You will find a very big restoring force. The problem with this geometry is that if you see its dynamics, if you remember in last slide, I mentioned that there's a parabolic trajectory that the beam's end follows, and this parabolic trajectory induces a rotation in the device. So this, as you see here, this can make the comps come into contact, and okay, so we don't want this in our device. So the second geometry that we study is the folded spring. This is the geometry that you go to when you are working with MEMS springs. So this geometry is good because it gets rid of these parabolic displacements. You have a beam that tries to move to the left, and this one tries to move to the right. So if you sum up these displacements, like they will sum up to 0, and you will see that the clamping and the shuttle, they don't move with respect to each other, at least not horizontally. So this is good, but the problem is that if you apply a perpendicular force to this geometry, you will see this kind of movement. Like you will not find a strong restoring force in the perpendicular direction, because there's an extra degree of freedom. These clampings, they are free to rotate as they are free to move. So this extra degree of freedom makes the perpendicular restoring force very, very low. It's a bit bigger than the one you would find in the vertical direction, but it's not enough for our application. So the last geometry that we came up with is the guiding beam. The geometry is very close to the folded beam. If you look at it closely, it's just half of a folded beam, but with the difference that instead of having free beam supports, like they are free to rotate in the folded beam, here we connect them by a rigid beam, so a guiding beam that we call it. And so this is nice because it's not as rigid as the opposing beam geometry, but it doesn't have this extra rotation. Like it has the same direction, direction of the folded beam, but this time we have a very strong perpendicular restoring force. Now that we know that for this geometry the main displacement is the one that engages and disengages the capacitors, we are going to reduce our model to a 1D model. So we're going to bring more forces into play. We're going to bring gravity, which is going to, as you see in the animation, is going to make an offset of the oscillation. And this will reduce the energy that we recuperate because capacitors don't engage completely. The second aspect that we want to see is to know which electric interface is the best for this device. So for this, we propose a very general circuit interface, which is the ideal charge pump, this one, that can emulate almost any rectangular cycle. So we're going to vary these two voltages in order to see which is the best configuration for our device. So we perform simulations on ngSpice in order to get the power output of our device for different configurations. So the first graph represents different configurations on the circuit interface. Each value of gamma represents a different topology of an interface. And why we see the power output. So we see that for gamma equals to 2, we have a maximum for almost of values of voltage, and this value corresponds to a Bennett Doubler. So this is potentially the best circuit for this device, where we'll get the most power out. And here on the right, we see different orientations of the device. So we go from 0, which is the gravity is parallel to the device, and we rotate it, and we see how this affects the power output. So we see we get a maximum in 250 nanowatts, where the capsule is perpendicular to gravity, and when it's parallel, we have 0.1 microwatts. So we lose about half of the power when we're facing gravity. So we found a geometry that engages and disengages capacitors without making them come into contact. We tested this geometry to see how much power we can get from it, and there are some works to do to find the good combination of parameters, because the power output that we want is higher than the one that we have now. But this is a question of parameter tuning. And finally, we are fabricating the device, as you see here in the pictures. We are in the last stages of fabrication, so soon we will be able to compare the theoretical predictions to the real-world device. So thank you for the attention, and see you soon.
Thank you very much for the presentation, and you're present here for questions. So let's start. We can discuss the paper. Are there any questions from the audience? So one question from my side. You showed on slide 7 this initial structure. First question was what was the reason to start with this structure?
You mean the one that rotates?
Yeah, exactly.
Yeah, like first we started from this geometry, because we knew that to load axially a beam is much more difficult than deform it perpendicularly. Like if you take a beam and you try to deform it this way, it will be much easier than this one. So we proposed this geometry and tried to study why, if it could work, and we saw that okay, we have a rotation because we didn't see at the very beginning. We saw this on COMSOL, and after we said, why is it rotating? Yeah, like after we saw that, yeah, we had an extra degree. I mean, we were not having an extra degree of freedom, but we had this rotation at the end, this displacement at the end of the beam. We say, okay, this one, no.
Okay. Yeah. So I have another question, but Abe, you have also one, please.
Yes, Peter, thank you. Very, very interesting device and really important problem. You did mention that really, the model that you worked with, it doesn't have enough power. I think a pacemaker maybe would require a few microwatt, and you are still in the 250 or so nanowatts. So you are still, maybe you still have a gap. And maybe that gap could be fixed by maybe changing the size of the harvesters. But do you have an idea about like the power density of the device? Like how much power can you get per unit area? Because that's a very important metric, for these applications. So do you have a number? Do you know what you need to target, for these harvesters?
Yeah, I mean, like we know that for the applications that we want, there are already, maybe you're speaking about microwatts, but there are other devices, low power devices that consume microwatts. So we are not that far. I mean, we are low, but we are not that far from the final goal, because our main goal, it would be to generate some, like, let's say between 10 to 100 microwatts. So we are 1 or 2 orders of magnitude. Yes, I agree with you. We're one or 2 orders of magnitude lower. but so we can fix this in several ways. Like the first parameter that plays, as you say, in power density is the mass that you add to the system, because like acceleration is the force, sorry, is mass times acceleration. So if you put a bigger mass, you harvest more energy, but at the same time you need to have bigger capacitors that would drive this mass. And for the MEMS application that we have, we just have 200 micrometers of thickness. So it's not that much to have a strong electrostatic force to pull the mass. So as you say, I haven't calculated the exact number of the power density, but I think I mean we can calculate it easily. Like we have, let's say, it's in the order of 1 microwatt over a surface or a volume, sorry, of 2 centimeters times. But we need to calculate. It's an easy calculation.
Yeah, sure. No, but the other question, I mean, the competing technology, you are doing an electrostatic one here, but the competing technology would be, the magnetostatic, using inductors, and people have been, also trying devices. So have you looked at the have you compared the two competing technologies, magnetostatic versus, electrostatic? And why do we have to go with electrostatic as opposed to magnetostatic?
So there are several, it depends on which one of you look at this, because we can say, okay, this technology is better for this reason, like this technology is better for this reason. So yes, electrostatic solution it has the drawback, let's say, that is, it has low power compared to other technologies. But the advantage that it proposes is that it's easy to integrate with CMOS technologies. And here in electromagnetics, first you have a magnetic field, you need a coil, which is difficult to...
We have bad audio quality. Do you have changed your setup?
No.
No? Okay. Maybe it's a problem on my side. So, the others can...
I hear very bad.
Okay.
Yeah, I have a little bit of a noise on my side also, Peter.
Okay.
What do you do? I mean, I would try to be
Okay, please proceed, Sebastian.
I forgot to mention. Yes, so like the electrostatic solution is easily scalable to industrial levels, because you have other MEMS technologies are easy. They can be upscaled easily to an industrial scale compared to other technologies. Yes, like PSO and...
Thank you very much. Thank you. Yeah, that's a good point. Thank you.
Okay, thank you. There is another question from Emil.
Yes, in fact, it's very curious, because Paco is just, well, he's not now in front of me, but on the everyday base time, he's really in front of me. And but I don't know exactly what he's doing, so I'm very pleased I was very pleased to hear your presentation. And just a question about your pacemakers. My knowledge about that is quite old. So I was in the, pacemakers have a battery. The battery is lasting not so long, so we want to prolong. And then you presented a very small capsule, but this very small capsule also will maybe have a battery. So maybe how big is the battery, and is your goal to charge and to make longer the battery life, or is it just to power completely the pacemaker by your energy harvester?
No. The idea is to assist the battery, to have both. Like it will make the lifetime longer. Like self-sustained. Like it will be enough power. That's a point.
Okay, thank you.
Okay, any further questions? So I have another one. So again, concerning the structures on slide 8, you showed this structure with this different moving modes. And for me, it looked like the result of a modal analysis. And do you have the corresponding frequencies for these two eigenmodes analyzed? And the questions, the following question is: do you also analyze higher eigenmodes for the final structure?
No. We all the analysis we did was static, but we should do another study about the modes as you mentioned. But this one, as we have a very low frequency, like the most likely mode to excite is the first one. So but the thing that we wanted to study here, it was just the direction of the forces. Like if we have a force like in this direction, like in the axis, will the comps will come into contact? That was like the answer we wanted to, the question we wanted to answer. But yeah, after the next step would be that one. To check the dynamic behavior of the structure.
Okay, thank you very much. Okay, no further questions. So thank you again for your nice presentation, and we can go to the next one. Our next speaker is Do-Young Ha. So he also presented the first paper, so I can make some introduction shortly. So it's with the Abdullah Gül University in Turkey, and it's a short talk, and it's also pre-recorded, and we can start now. And it's on electric actuators.
The title of my presentation is Quasi-Static Operation of Two-Axis Tilt Microscanners with Aluminum Nitride Piezoelectric Quad Actuators. Among various application fields of microscanners, my focus is biomedical imaging. And for the microscanner actuation, a piezoelectric one was selected for its low operation voltage. As a material, PZT has been most widely used for its high piezoelectric coefficients, but its lead content becomes an issue for various applications, such as biomedical imaging. On the other hand, aluminum nitride is a safer material, but its drawback is a low piezoelectric coefficient. For this reason, most of the previous aluminum nitride actuators have been operated in the resonance mode. But it has issue in the long-term reliability due to shift or drift of resonant frequencies. Therefore, it is necessary to develop actuator configuration for quasi-static operation of aluminum nitride material case. Here, we have an illustration of the proposed device configuration. It has 4 actuators, which are connected to the mirror through those hinges. For the rotation about x-axis, same voltage is applied to actuator 1 and 3, and then to 2 and 4, so that it can rotate like this. And for the y-axis rotation, the same voltage is applied to 1 and 2, and then 3 and 4, so that it can rotate like this. And for diagonal rotation, the opposite voltage has to be applied to 1 and 4, or 2 and 3, and the remaining actuators are not operated, and it operates like this. In the design part, the most critical parts are the hinge design. Here we have 2 hinge sections, lateral and the longitudinal ones. And if the hinge lengths are too short, then it limits the deformation of the hinges. However, if they are too long, then the translation from the hinge deformation to the mirror rotation becomes inefficient. So we have to find the optimum hinge length, and we have calculated the rotation angles through simulation for various hinge combinations. For example, if we want to have high theta x, then we can choose this hinge length combination. But due to the small theta y value for that hinge length combination, it results in this type of image plane. On the other hand, if we choose this area, then it will have this image plane. For our application, a square image plane is needed. That is why we found this area as an optimum. With that, the optimum hinge lengths were found as 199 and 78 micrometers. And at 50 volts, 4.4 degree of mechanical rotation is expected in both axes. And then the model analysis was carried out for the design, and the resonant frequencies found was 460 Hertz and 2 kilohertz and 6 kilohertz. Next, voltage applications were examined for 2D scanning, and these are the voltage maps for the actuators. The blue color indicates the negative voltage, and the red color indicates the positive voltage. For example, if you want to scan to this corner, then this voltage combination can be used. And if you want to scan to here, then this voltage combination can be used. Eventually, the 2D scanning has to be carried out in a continuous fashion. So these voltage applications were developed. With that, the most straightforward way is to apply the frequencies in this way. F1 is like the fast axis, and F2 is like a slow axis. With that, this type of raster-like scanning can be obtained. However, there is some dense area and a coarse area. So one can say that the distribution of the scanning is not even. To solve this issue, a Lissajous scan mode can be used. Here, as you can see, those two frequencies are close to each other. And one can use this Lissajous scanning to have more well-distributed scanning pattern. As a summary, the quad actuator configuration is proposed for a quasi-static operation of aluminum nitride piezoelectric microscanner. 9-degree optical scanning is anticipated in 2D with an amplitude of 50 volt. Lissajous scanning mode was examined via numerical analysis. Thank you for your attention.
Thank you very much. So now the paper is open for questions. I can't see any question for the moment, so I have one question. Can you explain on the application cases for these optical probes?
Do you have a more specific question?
What is a typical application for these optical probes? You showed on the first or second slide. You showed this structure, the entire structure of this optical probe, and you showed on the last slide the scanning modes. And my question is, what is a application? Is it in inspection in machinery or in medical applications? So maybe you mentioned it, but then I missed it. So
yes. So this is being developed for the project, the bigger project for the laparoscopy, and so this optical probe is intended to be entered inside the body.
Okay.
The microscanner is to create the scanning pattern from the tissue. Okay,
so it's for medical applications.
Yes, yes.
Thank you. And another question. So, do you have any investigations carried out about the robustness to ambient vibrations for this structure?
That is a very good point. I will keep that in mind. I see question from Andreas Voigt.
Yeah, I have a question. I wanted to know if the relation of the deflection angle and the applied voltage is linear, or if in the final fabricated device you have to calibrate somehow this relationship between deflection and voltage.
Well, I expect in the first degree it is linear, and it was so set up in the ANSYS, console environment. But there might be some nonlinearity, as you might have concern. So yes, that has to be, I think, considered in the reality.
Okay, thank you.
Okay, thank you. Any further questions? Abe, you have a question?
Yeah, thank you, Peter. Interesting device for scanning. I'm wondering, in terms of the mechanical design of these hinges, you mentioned about these two lengths, and you had a really nice visualization of how you selected, I think the L, exactly the L length, AV and I think, let me see, BH. The question that I have, once you fabricate these devices, will you get any sagging? Will you get any deformation because of the mass of the hinges that might actually impact your rotation angles ultimately for the mirror?
That's a good point. It might. I haven't looked into that part, but in the simulation, I didn't see a huge impact, so I didn't look into it. But that's a good point. I can go back and look into it. The hinge dimension, the width of it was I'm planning to follow. I'm planning to fabricate with piezo mounts from MEMSCAP. So I followed the design rule of the foundry service. This is an extra information. Yes.
Okay, very good. Thank you very much.
Thank you.
Okay. Any further questions from the audience? I can't see any question for the moment. So thank you again for your presentation.
Thank you very much.
And we will go to the next presentation. Our presenter is Sumia Purohit. Sumia received a bachelor degree in electronics and communications engineering from the Bhilai Institute of Technology in Gurgaon, India, and a master degree in sensor technology from the Defense Institute of Advanced Technology in Pune, India, in 2016 and 2018, respectively. She's currently pursuing a PhD degree from the Department of Physics at the Indian Institute of Technology in Hyderabad, and her research interests include the design and fabrication of MEMS devices, and the presentation is on perforated microcantilevers for MEMS applications. So we can start.
A very good morning to everyone. I'm Soumya Purohit, and today I'm here to present my work on comparative study of perforated microcantilevers for MEMS applications. This is the outline of my presentation. MEMS stands for Micro Electromechanical System. It is a technology that combines both electrical and mechanical parts to create a system with moving parts. Its characteristic length ranges from 1 millimeter to 1 micron. MEMS devices have different types of advantages, like it has very small size, very low power consumption, low cost. They can be easily batch fabricated in large arrays and can be highly resistant to vibration and shock. MEMS technology finds applications in various domains. Here are a few examples where the MEMS has found its applications like AFM, accelerometer, gyroscopes, bio and chemical sensors, MEMS mirrors, and RF switch. Because of its versatility, MEMS-based devices can be used for different types of sensors. We all know that microcantilever type structures which are fixed from one end and free at the other, are the most widely used components for MEMS and namespace devices. And along with microcantilevers, perforations, which are said to be small hole in the material, are also used in the MEMS for various requirements like low squeeze film damping, low stiction problem, easy release of the structure during fabrication, and so on. Therefore, the design and analysis for perforated microcantilever becomes important and interesting at the same time, as it gives us the estimation for the different mechanical and electrical properties of the design. In this work, a comparative study between perforated and non-perforated cantilevers is performed. Resonant frequency, static deflection, and pull-in voltage are studied and compared numerically for different designs. Therefore, a accurate determination of all these properties has been done to optimize the performance and reliability of the designs. In the numerical analysis, three types of perforations, circular, square, and hexagon, are assumed, and with radius varying from 2.5 to 14.5 micron with a gap of 30 micron between two perforations is maintained. Using the structural analysis in solid mechanics module in COMSOL multiphysics, resonant frequency and static deflection are calculated for the beam, and to calculate the pull-in voltage, electromechanics module is used. The table here shows the dimensions of the microcantilever, and on the left side we can see the beam geometry. Here is the flowchart showing the process steps for designing and analyzing the structure in COMSOL. First of all, the dimensions are selected, then the physics and study are selected. Here we have chosen solid mechanics and electromechanics module. Then the parameters and geometry are defined. Material and setting up the physics. Material here used is polysilicon, and then we do the finite element meshing, then the simulation, and finally the analysis of results. So here are the model geometries. Square, hexagon, and circular shaped perforations are arranged in this way, and these are the designs which are used for the perforated microcantilever, and they are compared with the non-perforated or the simple rectangular. This graph here shows the frequency analysis. So here we can see that as the hole size increases, resonance frequency also increases. And the macrocantilever with the hexagonal shaped perforations gives us the highest frequency of 34.5 kHz, and the simple rectangular beam with no perforations has the least frequency among all the designs. This graph shows the deflection analysis. So here we can see that as the hole size increases, the deflection also increases, and beam with the circular perforation gives us the highest deflection of 0.86 micron. And the perforations, we know that makes the microcantilever more flexible. As the hole size increases, the stiffness reduces, making the beam more flexible, and therefore the deflection also increases. This graph shows the pull-in voltage analysis. So the pull-in voltage decreases as the hole size increases. The value of the pull-in voltage for the square-shaped perforations is the least, and it is found to be 3.84 volt. So the pull-in voltage depends upon the stiffness constant and the area of the microcantilever beam. So as the hole size increases, the total surface area of the beam decreases and the stiffness also decreases. Because of this combined effect, the pull-in voltage also decreases as the hole size increases. Here in conclusions, this work shows the comparison of microcantilever with and without perforations, and the presence of multiple perforations influences the electromechanical characteristics. Perforation makes the cantilever more flexible, reducing the stiffness and the mass, therefore influencing the frequency and deflection. Therefore, it can be concluded that evenly distributed perforations on a microcantilever decreases the pull-in voltage and making it suitable for the development of low actuation MEMS devices. Here are the references that I have used for my work. Thank you everyone for your kind attention.
Thank you very much for your presentation. And we have time for some questions. Are there any questions from the audience? Abe, do you have a question?
Yes, Peter, I do. Thank you for the presentation. I was wondering from a mechanical viewpoint, are these Euler-Bernoulli beams that you have modeled or you have simulated, or Timoshenko beams?
No, actually, we have considered the Euler-Bernoulli beam. That's
okay.
We have.
Okay. Thank you very much for this clarification.
Thank you.
Okay, Emil, I can see your hand. Is this still from your command, or is does another question arise?
No, it's just that I didn't put down my hand before.
Okay. There is another question from Naga.
Yes, I wanted to ask you about the simulation software. Did you compare any other software than COMSOL or alone COMSOL?
No, we did only on COMSOL.
Okay, what about the electrostatic force for your device?
Yeah, we can compare it, but here I have only calculated the pull-in analysis. Like it's the coupled effect. So in the electromechanics part, we do the solid mechanics and the electrostatics. So voltage is what we see that it has the electrostatic force.
So you mean like there is no theoretical electrostatic force that you calculated for your device?
Not theoretically, but yes, we can do it.
Okay, but are you able to measure this electrostatic force in COMSOL?
No, I haven't explored it yet, but I think we can.
Okay. Thank you.
Thank you.
Okay. One question from my side. You showed on one slide this impact on the shape of the perforation, right? That was.
Yes, sir. Yeah.
I'm wondering, comes the impact on the behavior from the shape or from the different cross sections of the hole? So it's not quite clear for me. You had the dimension of the perforation on the x-axis, and from my point of view, this will result in different cross sections. And could you comment on this? Is it shape or is it on the cross section of the holes?
Basically, I explored the shape. So it's like we considered the circle as our reference, and then accordingly we put it should be like the same surface area. So within the circle, we put the hexagon, then we put the square. So according to that, we chose the total size or the side length of the square and the hexagon according to the radius of the circle.
Okay, so the different shapes have all the same cross sections, and you okay, so then so because the dimension was in micron on the axis, and so I wasn't confused about that. Okay, thank you very much.
Okay, thank you.
So I can see two hands, but I guess it's from the previous questions.
Actually, Peter, I do have another question, but it's now related to really the distribution of the perforation. I mean, you can have square, you can have a hexagon, but the way they get distributed, is it on a Cartesian grid, or is it on a hexagonal grid? Did you look at that impact also on the different metrics that you have measured? It's really the way the holes are distributed on your beam. When the hole becomes very small, then you have actually several possibilities in terms of the topology of the holes.
Yeah, actually, I explored only the way it's like on the axis, like on x-axis it is distributed, so we didn't explode it on the much depth, but definitely we can do it in the future analysis for this.
Okay, thank you very much.
Okay, thank you.
One last question.
Yeah, of course.
So is it possible to measure pull-in voltage simulation, or this is theoretical that you did? The pull-in voltage.
I didn't get your question, please.
A pull-in voltage that you are explaining, right, about the pull-in voltage. So it's about the theoretical or simulation one?
So this is the simulation one. Only rectangular we compared the analytical and numerical, and we didn't calculated it for the perforated one because here the stiffness constant will change. So again we have to do the theoretical calculation for that.
Okay, but pull-in voltage it's possible to measure in simulation, right?
Yes, we did it through like pull-in voltage calculation in COMSOL we have done.
Okay, so it is good if you also put some comparison of the theoretical and simulation.
Yeah, definitely.
Yeah, thank you.
Thank you.
Okay, any further questions? No, it's not the case, so thanks again for your presentation. And we are now at the end of this session on mechanical design. I would like to thank all speakers for their very interesting presentations. You have now the opportunity to meet all speakers in the breakout rooms. So you find it on the program. There is a specific link for the breakout rooms to where you can discuss in more detail, but you can also stay here in the plenary room. I would like to thank you all for joining us for this session, and we will proceed. You can see it here at 10:35 in the plenary room with the next session on sensors. So thank you very much for joining.
Okay, I think we are going to get started. Welcome back to DTIP. This is session 7 of DTIP 2021. The title of this session is Sensors. This session has 3 long presentations, 20 minutes each, and 2 short presentations, 12 minutes each. My name is Abe El Fadel. I am with the Khalifa University, United Arab Emirates. The temperature outside is only 38 degrees. And so it's cold, you know, as far as we are concerned. And I'm glad that I'm inside anyhow. So our very first paper is going to be presented by Cecile Guila-Houri. The title of this paper is High Temperature Gradient Microsensors for Skin Friction Measurement in Flow Control Applications. Cecile is the lead author of a number of contributors from various institutions in research institutions in France. And she's also the speaker. And let me introduce Cecile for you. Cecile Guila-Houri received her MS degree in engineering with specialization in micro nanotechnology, wave physics, and telecommunications from École Centrale de Lille in 2015 and began her PhD in November 2015, joining the ONERA, the French Aerospace Lab, and the IEMN, the Institute of Electronics, Microelectronics, and Nanotechnology of Lille. After PhD graduation in October 2018, she joined Centrale Lille as associate professor in September 2019 and IEMN UMR CNRS 8520 as researcher. I think this is maybe just the name of a research unit within CNRS. That's my guess. Her research concerns the development of microsystems, microsensors, and microactuators for fluid dynamics and aeronautical applications. With this, Cecile, the floor is yours. Please go ahead.
Thank you. Hello, everyone. Thank you for the introduction. So yes, today I'll talk about skin friction microsensors that we developed in the IEMN in the aim of flow control applications. And this project is done with numerous people, including some people from the UNERA, which is our main collaborator for this subject. So the general context of this research is the one of transportation systems with many issues like gas pollution, issues of safety, noise pollution, etc. And actually one of the potential solutions to address these issues is flow control. And flow control aims at modifying the flow behavior between the interaction with the flow and an object thanks to a space and time localized perturbation. And here you have an example of bus jet forcing the flow to be attached to an airflow model. And the aim of flow control, the major goal of flow control activity is to go to closed loop flow control, where you have actuators that impact the flow field and sensors that measure the flow field in order to have to give a feedback signal to adapt the command given to the actuators. And here at the IEMN, since we are a laboratory of microtechnology, we are working on developing new technologies of actuators and sensors for flow control. And yesterday, Thomas Arnould presented you one of our technology of microactuators, and today I will present one of our microsensors that we have developed. So first, for flow control, what do we want to measure and how do we do it? So we want to measure the flow-induced shear stress, also called skin friction, at the wall of an object. So it's a force, a tangential force, which is due to the flow viscosity. So here you have a little schematic for the shear stress, and it is by definition proportional to the velocity gradient at the wall. And the main sensors that were developed for measuring wall shear stress and flow velocity are based on thermal anemometry. The principle is quite simple. Actually, you have an electrically heated wire here, which is elevated at a temperature given T0 superior to the one of the fluid. And when there is a flow velocity, force convection induces decreases of the temperature. And you can add an electrical circuit in order to adapt the heating current in this wire to maintain the temperature constant. There are existing thermal flow sensors that were developed since many years, and two main designs were developed, hot film sensors and hot wire sensors. In hot film sensors, the wire is deposited on a substrate that can be flexible, and hot film sensors are then very particularly useful for shear stress measurements, since they are implemented at the wall of an object or in the wall of a wind tunnel, and they are very robust. On the contrary, hot wire sensors, in hot wire sensors, the wire is free in the flow field and only fixed by its two extremities to two prongs that you can see here. The wire is not really clearly visible in this photograph. But the advantage is that you measure the force convection quite well without by neglecting the conduction in the prongs. But it's more useful for flow velocity measurements, since you have an intrusive measurement in the flow field, and they are very fragile, so they may not be very useful for wall shear stress measurement, even though some people sometimes use them to measure the velocity close to the wall. The main drawback of hot films, contrary to hot wires, is that the heat transfer that you measure is a combination of force convection that we want to measure and also conduction in the wall. And actually, hot films cannot distinguish which is due to what. Okay, so now that we've seen what kind of sensor exists, for now, we can go to present our IEMN sensor, and that's I will begin with. And then I will present you some calibration, testing, and experiments that we've done in various wind tunnels, both in ONERA Lille and in ONERA Meudon. So I presented you the two existing thermal sensors, because our structure that we developed and patented at the IAMN is a kind of hybrid structure between hot films and hot wires, with the objective of having the advantages of both structures without their drawbacks. So basically what we have is a wall suspended wire. So it is separated from the substrate to have a thermal insulation, so that only force convection is measured, but it's embedded in the wall, as you can see in this simulation, so it can measure wall shear stress. And for a mechanical robustness, we added perpendicular bridges here, micro bridges made in silicon dioxide, which is a thermal insulator. And then the wire can be long without being fragile. And also, of course, since it's embedded in the wall, it's non-intrusive. So in red, you have the hot wire, which is also called a heater in literature, and which is the heated wire that is used for measuring the wall shear stress amplitude measurement. So to this design, we complexified a little bit the design by adding two lateral cold wires that measure the temperature distribution around the heater, as you can see here. And these two cold wires are used to detect the flow direction that corresponds to the sign of the wall shear stress, because the upstream wire will be more cool than the downstream wire, and then the difference of temperature gives us the sign of the wall shear stress. We fabricated and characterized the microsensors in the IAMN clean room. So on a 3 inches wafer, we can manufacture more than 100 microsensors. You have here a picture of the sensor chip. And actually, most of the space is used for the electrical contacts, and the sensitive part is only in this, it's 1 millimeter long, about, because well, here you have a zoom, it's a scanning electron microscopy photograph of the structure. You have the 3 wires here that reach 1 millimeter long for 3 micron wide. And you have the perpendicular micro bridges along the length of the wires in order to ensure the mechanical robustness of the structure. You have here a zoom on the sensitive part of the sensor with the 3 wires, the micro bridges, and you can easily see the cavity under the wires. So we moved to the Onera Lille to calibrate the sensor in the turbulent boundary layer wind tunnel. That is very well instrumented, so that we can deduce the wall shear stress exactly at the wall in this wind tunnel. So we could calibrate the microsensor. Here you have a photograph of the integration of our sensor in the wall of the wind tunnel, and we could measure the shear stress for minus 2.5 to 2.5 Pascal. And here you have the response of the microsensor. We could also measure the turbulent kinetic energy thanks to the frequency-weighted power spectral density measured by both the microsensor and also a Dantec hot film sensor that was used for reference. And we could get a bandwidth of about 15 kilohertz, which is good, but we want to go further and improve the electronics in order to have a wider bandwidth. To measure the full spectrum of the turbulent kinetic energy. Then we moved to the Onera wind tunnel, Onera Meudon wind tunnel, sorry, which is particularly interesting because it's a high Mach number subsonic wind tunnel. So we can have Mach number flow going from a Mach number of 0.5 to 0.8 about. To give a comparison, the former wind tunnel was going up to Mach 0.1 at the maximum velocity. So it's very higher speed flow while being subsonic. And we tested the sensor in 2 positions, in an upstream position and downstream position, because in a wind tunnel, the shear stress is always more important in upstream position than in downstream. And we can see actually the result here and see that the response of the sensor is higher for the upstream position than the downstream one, with a quite linear response, which is quite good and what we wanted to see in this configuration. And also the sensor resisted to very high speed flows, even if remaining subsonic. And finally, I will present some experiments that we done of flow control, and more precisely flow separation control. So what is flow separation? It's it's a phenomenon that occurs in vehicles, for example, in aircraft during takeoff and landing. And it's a phenomenon that can be very dangerous, and also that the main, even if not dangerous sometimes, it increases a lot drag. So it's responsible for a higher consumption of energy and fuel consumption. It occurs also on ground vehicle by increasing the drag at the rear of the vehicles. It is characterized by backflow that separates the boundary layer from the subsurface of the object. And as we regard the wall shear stress, for an attached flow, the wall shear stress is always positive. When we got to the this flow separation point, the wall shear stress becomes equal to 0. And then when the flow is separated, it is negative because of the backflow. Therefore, our microsensors are particularly useful for detecting flow separation. And this is the objective of this experiment is to detect the flow separation, but also to control it. And how controlling flow separation? It's by adding momentum to the flow in order to re-energize the boundary layer and stay it attached, avoid the separation, or reattach the boundary layer that was separated. And for that, we can use fluidic jets. So here is the presentation of the experimental configurations. So we have a flat plate here, and here we have a flap, which has the profile of an airfoil. So here's the reference of the airfoil profile, and we integrated 12 sensors on the flap. And you can change the angle of the flap in order to force separation to occur. And we have pulse jets in that are blowing on the surface of the flap. So the pulse jets are Festo MEH2, so it's not a micro actuators like the one Thomas presented you yesterday. And we equipped the flap with 12 microsensors. So 2 are in individual packaging, as we call it, because we have an individual electronic card for each sensors. But due to the space available in the rest of the model, we developed an array of a flexible array of 10 microsensors with the electronic at the backside. So it's common electronic and controlling both 10 sensors simultaneously. Sorry. So the objective of these experiments were first to see the separation that occurs on the flap when we increase the angle. So it's going from the trailing edge to the leading edge. And also to see the effect of the control when the pulse jets are blowing. So here are some results. So first, let's focus on the 3 yellow sensors. So it's 1 sensor at the leading edge, 1 at the trailing edge, and 1 in the middle. And with these 3 sensors, we can see the flow separation point moving from the trailing edge to the leading edge by measuring the variation of shear stress with respect to the flap angle. And as you can see here, in blue, it's the trailing edge sensor, and the shear stress becomes equal to 0 at around 10 degrees. And after that, it becomes completely negative. So the flow separation point is detected as 10 degrees. Then in red, you have the value for the middle sensor that detected flow separation at 13 degrees. And finally, at the leading edge sensor, we detected separation at 18 degrees. So a direct measurement gives the flush separation point. In this result, we focus on this sensor, the second sensor from the leading edge, and we measured the variation of shear stress in two configurations. Without control, it's in blue, and with post-jet control in red. So in blue, we have almost the same result as for the leading edge sensor 0.2, here in black. So the flow separation point is detected for around 17, 18 degrees. And when we add the post-jet control, we can see that the shear stress stays always positive for all the angles. So the flow is not attached, separated. Sorry, it's attached for each angle of the flow. However, we can see that for the low angles, since the flow was already attached, we have more shear stress that is normal due to the actuation system. So we detected the effect of the control. So with a closed loop control, the idea is not to use the actuators for up to 15 degree or almost 15 degree, and then use them to stay attached for all the angles of the flap. So I will now give some point of conclusion. So I presented you our calorimetric microsensor, which has hybrid structures between two existing microsensors, well, sensors and microsensors for flow measurements. I presented you also its calibration and the measurement done in turbulent flows, both for low speed and high speeds. And finally, I presented you our first active flow control experiments using these sensors as a measurement tool on this flap model. So we successfully detected separation and see the effect of the control with post-jet actuation. But this was open loop active flow control experiments, and so for perspective, we want to go into the closed loop flow control on the flap model. Also, I said to you that we want to improve also the bandwidth of the sensor in order to get the turbulent kinetic energy spectrum for various velocity flow. Since when you increase the velocity of the flow, the spectrum is shifted to a higher frequency. And also in the framework of a new project, which is the ANR Astrid Maturation Chemical Project, we want to implement the microsensors on real vehicles and in real conditions too. And this project is done also in collaboration with the UNERA and also with CKPM, which is a company that owns several kind of aircrafts. And we will implement the microsensors on this kind of real vehicles, namely slow plane and high-speed aircraft. So thank you for your attention. And if you have any question, I'll be very happy to answer them. Thank you.
Yeah, thank you very much, Cécile, for this very interesting presentation on this very interesting sensor. Are there any questions from the audience? We have a few minutes for questions. Please go ahead and raise your hand. I see a few hands raised. I'm going to start with Andreas Voigt. Please go ahead, Andreas, and ask your question.
Yeah, hello. Thanks for the interesting talk. I have one question. I've seen that in your sensor, there is a small pit below the wires. And I wondered if this pit somehow can influence the flow, if you have made an estimation that this pit does not disturb your flow.
This pit is about a 10 micron deep. But since the sensor is at the wall well, it's integrated at the wall, the velocity is very low, so there is not really an impact of this pit, this cavity on the flow.
Okay, thank you.
And actually, it's very useful because the flow only sees the wire without seeing. I mean, the heat transfer is enhanced thanks to this capability.
Mm-hmm. Thank you.
Okay, thank you very much. Next in line is Emil Martinchik. Go ahead, Emil.
Hello, Cecile. I just got question on your design. So you have a hot wire in the middle and two cold wires by the sides. That's okay for me. But I noticed that you have silicon oxide and the hot wire is up on the top of the silicon oxide and the cold wires are below. And why didn't you make all the three on the same level?
That's because the structure is a little bit more complex that I've presented here because of time, but I will go back to the schematic. Actually, our electronic is a bit different from the one that is used commonly in thermal sensors. In thermal sensors, you have, the measurement is done by the wire which is heated. This is not the case here. We uncoupled heating and measurement. So here actually, if I don't know if you see well on this schematic, but you have in red the hot wire. So where we have the heating current, and under this hot wire, we have in a yellow wire, which is a measurement wire. And actually, we have a very thin layer of silicon oxide between them to electrolyte insulate them. And we use the measurement of this yellow wire to adapt the current in the red wire.
Okay.
It's just to improve the signal to noise ratio by uncoupling heating and measurement, two different circuits.
Mm-hmm. Okay, it was not visible in your drawing, and it's a really nice detail. Thank you very much.
Okay, thank you very much. I see Etienne Poyo with a hand raised. Go ahead.
Yes,
go ahead, Etienne. Yes.
Thank you. The convection coefficient of air should vary with the humidity level. Did you try to test the influence of humidity?
Not now. I don't have the equipment. I am going to make these experiments, but we just have the equipment just a few weeks ago, so it's ongoing work. But actually, it is a point that needs to be measured, and it is one of the drawbacks of thermal sensors, but all kinds. Actually, in wind tunnels, when we are doing experiments, temperature and humidity are two main factors that we need to have in mind to compare to experiments.
And what about when you will test your sensor on a real aircraft?
Yeah.
The surface can be frozen, so in high altitude. So do you have plan to avoid the influence of freeze on your structure?
Actually, it's it's heating. So it's heating at plus about 100 degrees. So even if it's freezing and minus 50, let's say, the heater will be at plus 50. Okay.
So it should be good.
It's the point in thermal sensor is that what we measure is a difference. It's always a variation, not absolute measurement.
Okay. Thank you.
It's exactly like you have in your car windshield, right? You know, these are the wires that you use to de-ice the windshield. Yeah. They will de-ice the wing, you know, in the same the same
they
effect.
are very small.
Exactly. Thank you very much. Any more questions before we move to the next presentation? May I ask, so I don't see any more questions. I'm going to ask a very quick question, Cecile. You made a point that this sensor actually does the the shear stress measurement and the direction, right? You know, it can figure out the direction of the flow. Where did you use the direction measurement? Was that in the attachment and the flow attachment to the wing? Is that where this flow direction could be useful? Or
yeah, because the separation is very characterized by this backflow here, and the shear stress becomes negative when the flow separates.
Okay.
So by measuring the sign of the shear stress, we can see directly if the flow is separated or not.
Okay, very interesting. Thank you very, very much. Okay, so with that, I would like to thank the speaker for a nice presentation. And we're going to move to the next talk in this session. It's entitled Development of a Bio-Inspired Angular Acceleration Sensor towards the non-invasive investigation of inner ear pathologies. And the lead author and the speaker is Etienne Pouillot from INL. I think it's in Lyon, France. And Etienne received his master's and PhD degrees in physics from the University of Bordeaux, France, respectively in 2007 and 2010. During his PhD, his research activities were focused on the thermal characterization of individual silicon nanowires by using atomic force microscopy techniques. After 2 years of postdoctoral research on the development of nanostructured solar cells at LMGP in Grenoble, he was recruited in September 2012 as an associate professor at the National Institute of Applied Sciences, INSA of Lyon. He is currently working as a researcher at the Lyon Institute of Nanotechnologies, INL, in the electronic devices group. His fields of interests in the field of flexible electronics, and they are oriented towards the integration of nanostructured strain sensors and resistive memories. With this, Etienne, the floor is yours. Go ahead.
Hi, everyone. My name is Etienne Pouillot. I'm working as an associate professor at INSA de Lyon in France and doing my research activities at INL, Institut des Nanotechnologies de Lyon. Today, I'm going to present the paper entitled Development of a Bio-Inspired Angular Acceleration Sensor towards the non-invasive investigation of inner ear pathologies. This work has been carried out in the framework of a project in collaboration with colleagues from Mathéis Laboratory, located in Lyon, in France, and with colleagues from Institut de l'Audition from Institut Pasteur. After a short introduction, I will first present the integration of the angular acceleration sensor and then its electromechanical response analysis. As you can see on this schematic view on the left, the human ear consists in 3 parts: the outer ear, the middle ear, and the inner ear. This work addresses only the inner ear, that is a complex membranous sensory organs of about a few centimeters in size. As you can see on this 3D image on the right, the inner ear integrates 2 sensing structures. Here on the left in yellow, the coil cochlea that provides auditory function, hearing sense. And here on the right in gray, the vestibular system that provides balance function to humans. The vestibular system, here on the left, hosts 5 sensors that are able to detect angular and linear accelerations in all directions. In particular, the vestibular system integrates 3 semicircular canals perpendicular to each other that can monitor rotational head motions. As you can see on this simplified view on the right, the semicircular canal system is filled with a fluid called the endolymph. It also integrates a soft membrane, the cupula, and an electromechanical transducers composed of kinocilia and vestibular hair cells that are directly connected to the vestibular nerve. Under rotation with respect to the symmetry axis of the canal, the displacement of the fluid, the endolymph, deflects the membrane, the cupula, and activates hair cells to transfer the information to the vestibular nerve. The semicircular canal system is especially responsible for the vestibulo-ocular reflex that helps to stabilize head and gaze motions, and it is essential for the perception and control of movement. Today, it is estimated that about 20 to 30% of the global population suffers from balance disorders that are due to defects of the vestibular system in 85% of cases. Because of the fragility, complex structure, and microscopic dimensions, often no treatment is proposed, as the benefit-risk balance is considered too high. In this context, our long-term objective is to develop a realistic physical model, an artificial vestibular system, in order to investigate different specific pathologies of the inner ear, in order to find new treatment procedures. In literature, several numerical models that describe the fluidics of the semicircular canal were proposed these past 10 years, but the data collected from this model were never compared to a physical model. Here I have presented two examples extracted from literature. Here on the left, it is an illustration from the work of a Portuguese group located in Porto that was interested in the vestibulo-ocular reflex rehabilitation. And here another example on the right from Isae Supaero in Toulouse, France, interested in the understanding of balance trouble that encounter fighter plane pilots under operation. Concerning the physical models, few biomimetics gyroscopes were presented in literature, but with morphologies that are a bit far, that differ from the real morphology of the inner ear. So in conclusion, there is still some work to do to get a physiologically realistic model in order to help clinical medicine to find new treatment procedures. Concerning our objectives, our short-term objective, and this will represent the main content of my talk today, was to validate the angular acceleration sensor function in a simplified geometry that is a bit far from the real physiology of the vestibular system. But we want to underline the fact that in the long term, in the next coming months and year, our plan is to implement an original process based on 3D printed molds in order to develop replicas of real organs, starting from CT scan images of real organs. From this realistic model, we hope in the future to investigate different specific pathologies of the vestibular system. We also plan to simulate the semicircular canal surgery in order to refine the operative gesture. And finally, we are convinced that the development of a realistic model could be used as an educational tool for academics and hospital practitioners. Okay. As you can see on this photograph, our prototype is made from a plexiglass piece that presents the pattern of a circular canal at scale 10. The plexiglass piece was designed in two symmetrical parts that are stuck and made airtight so it can be filled with a fluid to model the underlength. We have also provided a lateral slot here in order to insert within the mockup an electromechanical transducer to model the cupular hair cell system. This transducer is based on a flexible piezoresistive cantilever that is connected to a PCB. As you can see on the bottom here, this is a photograph of the complete system. We have introduced the piezoresistive cantilever within the lateral slot here, and we have stuck it by using a silicone paste. After complete drying of the paste, we have filled in the canal with deionized water through two holes that were drilled on the top of the mockup. And finally, we have sealed the system by using an adhesive tape. Concerning the elaboration process of the piezoresistive cantilever, we have developed a very simple two-step process that is depicted here on this schematic. We have first integrated by e-beam evaporation a 10 nanometer thick palladium layer on top of a 75 micron thick polyamide substrate. Then we have used UV laser marking to pattern the cantilever geometry and also to pattern the piezoresistive elements and electrical pads for connection to the PCB. To develop the laser marking process, we have used an industrial equipment that is available at INL in our clean room. We have used a UV laser with a wavelength of 355 nanometers, an average power of 0.8 watts, a repetition rate of 15 kilohertz, and a scanning speed of 80 millimeters per second. Here on the top, I have presented a photograph of a substrate that integrates 12 cantilevers with different geometries. To develop these 12 cantilevers, it takes around 3 minutes with this laser marking process. In our mockup, we have integrated a cantilever that integrates two thin legs that have a length of 1.25 millimeter and a width of 300 micron, and a total electrical resistance in series of 2 kilo ohms. Before to insert the cantilever within the mockup, we have characterized its sensitivity to strain in a bending configuration. As you can see on this photograph on the left, the cantilever was fixed in a vise, and we have applied a non-deflection at its extremity by using a motorized actuator. Here on the right, I have presented the electromechanical response of the cantilever. Here I have plotted the relative variation of resistance of the cantilever as a function of the deflection level, up to 500 microns in tensile and compressive strain. As you can see from this graph, we could get a roughly linear response over the full range with a sensitivity coefficient of around 2.5 per meter. Concerning the electromechanical response of the complete system, we have first tested it to pulse rotational excitation. Here I have prepared a short video that presents a simple experiment performed by hands. Here on the screen, you can visualize on real time the electrical resistance of the cantilever recorded with a source measurement unit. You can see here on the graph several spikes, negative and positive resistance spikes that are due to the rotation of the mockup around the vertical z-axis. Then, when the mockup is rotating around the two horizontal axes, you can see here on the screen that there is no resistance variation. So this means that our system is only sensitive to one rotational axis, the z vertical axis. Then you can also observe that we can get negative or positive resistance variation depending on the direction around the z-axis. And this is simply due to the fact that in one direction, the piezoresistive cantilever is set in tensile strain, and for negative variation under compressive strain. This slide summarizes the results obtained from the previous experiment. Here you can see on the left the orientation in space of the mockup with the three space axes. And here on the right is the resistance of the cantilever over time for different rotations. And as I said before, in conclusion, from this experiment, we could validate that the biomimetic system only responds to one rotational axis, the vertical z-axis. And we could also demonstrate that it is sensitive to the rotational direction. Then we have tested our system under forced oscillation with sine rotational excitation. To do this experiment, we have placed the system on a swivel chair that is used in hospital to diagnose vestibular diseases. So this experiment was performed in the Edouard Herriot Hospital in Lyon. Here on the right, I have presented the angular position of the chair that is oscillating over time to the cantilever resistance. We have tested the response of the system under forced oscillation at 3 different frequencies that are specific frequencies of the vestibular system. And from this experiment, we could validate that our system properly responds to the medium vestibular frequencies. To deeper analyze the response of the system under forced oscillation, we have compared our data to the Steiner-Sen model that was developed at the beginning of the 20th century. The Steiner-Sen model describes the subsequent canal dynamics as a strongly damped torsional pendulum. As you can see here from Newton's second law, you can get this equation, where m is the mass of the fluid, x the position of the fluid in the middle of the canal, and c the canal wall position. In this equation, you can see that we have two terms. Here, the viscous drag of the fluid inside the canal, and here on the right, the elastic force exerted by the cupola on the fluid. By rewriting this equation as a function of the cupola deflection d, by assuming that the deflection is equal to the difference between the fluid position and the canal wall position, we could get this equation. And by solving this equation in permanent regime by using a complex formalins, we can get this solution with dm the deflection modulus under force oscillation and phi its phase. Finally, the cantilever resistance is expressed as a linear function of the deflection level of the cupola of the cantilever. In this equation here, you can recognize the sensitivity coefficient alpha that was extracted from the experiment performed in bending configuration. And R0 represents the resistance at rest of the cantilever. So we have compared our data to this basic model at 3 different angular frequencies, ranging from 1 radian per second to 4 radian per second. We could get a fairly good agreement between our data and the model at the 3 different tested frequencies. From this experiment, we could extract 2 parameters: the eigenfrequency of the system, that is ranging from 3 to 5 radian per second, and also the damping coefficient of the system, that is ranging from 100 to 200 per second. We have also compared these extracted parameters to clinical data from literature and could get a good agreement. And this is a really good point because it confirms that our system properly responds to the expected vestibular frequencies. So in conclusion, we have developed a prototype from plexiglass blocks that presents the pattern of a semicircular canal at scale 10 with a simplified geometry. We have also developed a 2-step process to integrate flexible piezoresistive transducers to model the cupola SL system. We have also demonstrated that our complete model only responds to one rotational axis, and it is also sensitive to the rotational direction. And finally, we could validate that under forced oscillation, the bio-inspired system responds to the expected medium vestibular frequencies. So now I am done with this talk. I thank you very much for your attention, and please don't hesitate if you have any questions. Thank you.
Thank you very much, Etienne. We are going to open the floor for maybe one or two questions at most, and that's because we are about 5 minutes behind schedule. So I don't see any hands raised. Andreas, go ahead. The floor is yours.
Yeah, thanks for the interesting talk. I have a question about the scale 10 that you mentioned. How was it motivated? Is it due to current fabrication limits?
Yes. So this is a starting study. In fact, we have launched this project last year. So to avoid any difficulties related to elaboration process, we choose to use a large scale 10. But sure, we want to reduce the scale down to 2. Would be good.
It's the size of the cantilever that's difficult to minimize.
We can reduce it quite a lot, in fact, with the laser marking process. Yeah.
Okay. Thank you.
Okay, one more question from the audience. If not, maybe I'll ask it. Etienne, this is a 3-dimensional rotation sensor. Am I correct? To
get a 3D.
3D vector.
You need a 3 canal.
Exactly.
Yeah.
So what you did is really just one.
Yeah, it's just one axis. Yeah,
one axis. Okay, thank you very much. I just wanted to clarify this.
Yeah.
Thank you very much. Okay, so with that, I'd like to thank the speaker again, and we are going to move to our next presentation in this session. And this is a paper that's entitled developing MEMS electric current sensors for end-use monitoring of power supply, and a non-linear correction scheme. And the presenter is going to be Minghua L from Jilin University in China. And Minghua received the BS and MS degrees in mechanical engineering from Jilin University, Changchun, China in 2019 and 2022 respectively. He was with Professor Dong Wang at Microengineering and Microsystems lab of Jilin University. His current research concentrates on cantilever current sensors and their engineering applications. Minghua, go ahead. The floor is yours.
Dear professors and scholars, my name is Lü Minghua, come from Jilin University. It's my great honor to present developing MEMS electric current sensor for end-use monitoring of power supply. Part 11, a nonlinear error correction scheme. Now I will introduce it from the following 5 sections. Section 1, Research Background. Our team forward the concepts of cantilever current sensor CCIs and did a lot of work in the direction of cantilever current detection. The first part is a piezoelectric cantilever current sensor with passive non-invasive and processing-free. Then, a passive AC-DC current sensor methodology for diverse metalline caps. It has 2 outputs, photoelectric and piezoelectric, and can measure metal-wire AC and DC current. And we also studied the active cantilever current sensor and the cantilever current sensor using TMR as the sensing unit. Section 2, Working Principle. The business principle of the cantilever current sensor is shown in the figure. The cantilever is fixed with a piezoelectric form and the end is fixed with a magnet. When the wire is energized or closed, a magnetic field is generated. The magnet is forced to vibrate the cantilever, and the piezoelectric form outputs a voltage signal. Next, Section 3, Nonlinear error. It can be found that the output voltage increased linearly with the correction. However, the cantilever will vibrate when the two-wire appliance is energized. Then the distance d between the cantilever and the two-wire appliance can steadily change. So the above linear relationship is unmirrored, which leads to the generation of the nonlinear error in the system, like figure, and decrease the measurement accuracy. As the current increased, the amplitude of the cantilever is also increasing, which cannot be ignored anymore comparing with the distance between the cantilever and the two-wire appliance. Therefore, the greater the measured rate is, the greater the measurement error is. When the nonlinear error is considered, the actual distance between the cantilever and the two-wire appliance Z 等于 Z0 减 delta Z。Z0 is the initial distance between the cantilever and the two-wire appliance, C is the amplitude of the cantilever. We can get the impression of the nonlinear error as follows. The relationship between the nonlinear error and the amplitude distance Z0 is shown in figure. At the same time, the sensitivity of the system will change with the distance between the cantilever and the two wire planes, and it can be deducted from the above formulations as follows. Black line is the rate of the wire, which means that the curve on the right side of the black line is real. It can be found that the nonlinear error decreases with the increase of Z0, but also with the decrease of the sensitivity. In this case, increasing the magnetic induction index can make up for the decrease of the sensitivity. In combination with the above scholar scheme, we can increase the initial distance to reduce the nonlinear error while monitoring of the original amplitude and sensitivity. As shown in figure, point A represents the state of the system. Point 2 represents the state at which the distance increases. At this point, the error will be decreased, followed by the significant reduce of the sensitivity. Point C indicates the state after increasing the magnetic introduced on the basis of point B. After this process, from the point A to the final point C, the error can be decreased while maintaining good sensitivity. Section 4. Experimental analysis. The experimental device is shown in figure. The magnetic introduction is changed by varying the number of magnets fixed on the end of cantilever. DC power supply and the electronic lines are connected by wire to adjust the current, and the oscilloscope is connected with the piezoelectric layer to observe the change of the output voltage. In the experiment, the Planck value of the output voltage is taken as the measured value when the current is turned on or turned off, as shown in figure. Then we change the number of magnets fixed on the end of cantilever and test the output voltage when the current is turned on and off from 1 to 6. The calculator results are shown in figure, and the graph includes the comparison between the theoretical results and the experimental results. It shows that whether the current is turned on or off, the output voltage always has a green trend with the increasing number of focused magnets. It is obvious that the sensitivity of the sensor can be improved, but the linearity of turning on is obviously better than the result of turn off, so it can be used as the output of sense. However, in the satiety result, the output voltage is nearly increased with the magnetic introduction, where in the experimental results of the output voltage is not completely nearly as the magnetic introduction increased. This may be caused by the increased mass of magnetic as number of magnets is increased, so that the measurement equator of the sensor is affected. Table and figure show the linear error of the three cases when different currents are passed in. It can be found that the larger the current is, the greater the nonlinear rate L8. When the distance increases from 3.5 to 5.5, where the current is passed to at 6, the nonlinear error is decreased from 47 to 32. When the magnetic introduction increases to a center digit, the nonlinear error can be greatly reduced. Section 5. Conclusion. For the nonlinear error, it is caused by the vibration of the cantilever when the two-wire appliance is energized, and the error can be reduced by increasing the distance between the cantilever and the two-wire appliance, but the sensitivity of the cantilever current sensor CCIs is also decreased. In this case, it is possible to compensate for the decrease in the sensitivity by increasing the magnetic introduction intensity of the magnets located on the cantilever, and the effectiveness of the scheme has been proved by the experiments. In combination with the above scheme, the nonlinear error can be reduced where the sensor maintains good sensitivity. The scheme is not only applicable for the DC environment, but also has implication for the nonlinear problems of AC environment and other variable structure. And then the part 2, for the first time, the Mendel location is published in press DC current decretion sensitivity, and we post a churn cantilever, a very high sensitivity DC current detection device. The magnetic field around the DC induce subjects the magnet to a severe magnetic force would interfere with the cantilever air and create the model locations to increase the then part 2. For the first time, model location is applied to imply DC current detection sensitivity, and we post a churn cantilever air here. Sensitivity DC current direction device. The magnetic formed around the DC conductor subjects the magnet to a straight magnetic force when it interferes with the cantilever aware, and cause the model location to increase the amplitude of the cantilever. In present study, the vulnerability of the post-DC crash detection divorce is described both ancestry and experimentality. Finally, thank you for the members of the GML team for their support and help. Thank you for your attention.
Okay, thank you very much for your presentation, Minghua. Let's open the floor for a couple of questions.
I suspect that Minghua is not attending the session, so
He's not. Okay.
We can skip the questions.
Okay, I didn't know. Okay, so let's skip the Q&A for this presentation and move right into the next presentation in this session, which is entitled Microthermal Anemometer for Turbulence Measurement, Development, Fabrication, and Characterization. The lead author and the speaker on this presentation is Baptiste Baradel. Baptiste is a PhD student at the ONERA Toulouse, and he's working in collaboration with the IES Montpellier on microthermal anemometers. So Baptiste, the floor is yours.
Okay, let's do it like this. So thank you for the introduction. So I'm Baptiste Baradel, PhD student at the ONERA Toulouse, and working in collaboration with the IES Montpellier on the development, the fabrication, and the characterization of a microthermal anemometer for turbulence measurement. So this research project is positioned in the study of turbulence flow as, for example, turbulent boundary layer in one tunnel. And this type of flow is the addition of numerous eddy scales, and for a full understanding of these flows, we need to detect all the scales, but the smallest one can reach value well below the millimeter under some condition. The most common technique to measure velocity in this type of flow is the hot-wire anemometry, as in it has been presented this morning, but I will do it quickly once again. So we have the sensing element, that is a metal wire that weighted it by Joule effect and placed in the flow. Then the flow will influence the wire temperature by forced convection, and through an appropriate probe calibration, we can estimate the flow velocity. The main problem of this type of probe is their too big dimension compared to the turbulence at this scale. Sorry, and this can lead to spatial and temporal filtering of some quantity measured. And according to works on hot-wire anemometry, the best way to avoid this filtration issue is to miniaturize the sensing element. And recently, the Princeton University managed to build such a miniaturized probe with very thin dimension for the sensing element. And this probe provides very encouraging results. So building on this past works, we attempt to build a microthermal anemometer also, but this time with reduced with a different design and simpler fabrication techniques. So here you can see the design of our probe is based on the freestanding thin platinum wire placed in the middle of a long bridge supported by a silicon structure. So as you can see here, this design will not allow profile shape for our probe, but this choice was made to use simpler fabrication technique, as I said before, and the position of the platinum wire in the bridge will permit us to reduce the prong influence during measurements. And finally, according to the lab knowledge, this design will give us a robust probe. So here we use a stacking of different material layers for our substrate for the manufacturing process. Starting by the top, we have some platinum that acts as sensing element. Then we have some silicon nitride. It is the main choice we made for the materials because it acts first as an electrical insulator between platinum and silicon, but it will also ensure the robustness and the flatness of the long bridge that we see before. And finally, we have the silicon, which is the main material for the probe and will ensure the mechanical structure. So to give the probe its final shape, we use some microfabrication techniques to pattern platinum and silicon nitride layers. We use simply photolithography and dry plasma etching. And to etch the silicon, we use the wet etching solution. Actually, we use potassium hydroxide, KOH, for the 3D GEP. So here you can see the final result of our probe. Here against a commercial probe, and as you can see here, the clear difference between the size of the sensing element between the both probes. So let's talk now about quickly about the performance of the probe. So when we perform the electrical characterization, we put forward improvement on the thermal coefficient of our probe compared to other micro anemometers. And this is even more reinforced by the fact that these thermal resistive parameters do not vary after hours of aging or after hours of measurements. And the most important is the measurement characteristic of this microanemometer. So here we put forward a night frequency response with a frequency cutoff 4 times superior to commercial outliers, and also with a good robustness to airflow. Actually, no breakage appear under 50 meters per second for speed, but we didn't reach the speed breakage, so we will see later. And the most important result that we put forward is the improvement of the detection of small quantities. When we performed turbulent boundary layer measurements, we identify that our sensor better detects small fluctuation in the inner region. Or this can be seen on this figure. So to conclude, I've presented you a new prototype of microanemometer manufacturing with simple fabrication techniques and compatible with the existing electronics. And according to the encouraging results, that leads to very good perspective for the future of this work. Thank you for your attention. And if you have any question, feel free to ask.
Okay, thank you very much, Baptiste, for your presentation. And yes, we do have a few minutes, maybe a couple of minutes for questions. Anyone who would care to ask a question? Please raise your hand. Go ahead, Cecile.
Hello, thank you for your presentation. That was very interesting. I have a question about your the resistance value of your wire. Have you measured it?
Yeah. The cold resistance is about 100 ohms.
And so it was compatible with what kind of electronics? Dantec?
Yeah, we use classical Dantec constant thermal anemometer, CTA, but the bridge is in a symmetric bridge, not 120. I don't know if you understand what I'm saying, but
in the electronics, so you had to adapt a little bit for your resistance value.
Yeah, we just
contact hot wires are more like 15 ohm.
Yeah. We use an external resistance for to put the overreach ratio the condition that we wanted.
Okay.
We cannot use the resistance of the conditioner classically.
Yeah. Okay. Thank you.
You're welcome.
Okay, thank you very much. Any more questions for Baptiste? I see Andreas. Go ahead, Andreas.
Hello. Thanks for the interesting talk. I wonder, do you have an application in mind that you want to apply your sensor next, where it would fit very nicely? Do you have any plans to use it now?
Actually, we wanted to test in overflow condition and test over designing, over size of sensing element to clearly see the limitation and the potential of this sensor. So will be classically more turbulent Bourdais layer measurement again. And we wanted also to test it in for thermal measurements, for temperature measurement. Yeah.
Okay, so you still want to validate it basically at this
yeah.
Okay, before you want to apply it to a real use case.
Yeah.
Okay, I see. Thank you.
You're welcome.
Okay, so thank you very much. Cécile, is that another question from you, or is that your old question? That's another question.
It's
go
another
ahead.
question if I
Okay,
can.
please go ahead.
Thank you. I was just wondering about the time, the bandwidth of your sensor. Have you tried to measure the turbulent spectrum in your wind tunnel?
Sorry, I didn't understand what I
was.
No, it's I don't hear. Sorry.
I was wondering about the time response of your sensor. Have you tried to measure the turbulent spectrum in your wind tunnel to see if the turbulent kinetic energy can be measured as a well, I mean, hot wire probes are used for that too, to see the dynamics of the
yeah, actually we did it, but I'm not present all the result in 7 minutes.
Yeah, sure. And what was the bandwidth that you managed to have? How wide was it?
Oh no, we didn't did it like this. No, I cannot say you.
Okay.
Okay. No. No. So okay, I did not. I did not.
Maybe we can use the breakout room for a deeper discussion on this bandwidth and response time issue. But a really good question. So with that, I would like us to thank the speaker again for his presentation, and let's move to the very last presentation in this session. It's entitled "Compensation of Perturbative Effects on a Thrust Measurement MEMS probe for Electric Propulsion." The lead author and the speaker on this presentation is Séverin Astruc. And did I pronounce it right?
Yes, it's good.
Okay, very good. Thank you. And Séverin received the master's degree in nuclear engineering from the engineering school Telecom Physics Strasbourg, France, in 2020. Since then, he has been with the French National Aerospace Research Center, ONERA, Palaiseau, France, where he is currently a PhD student. He's developing sensors for thrust measurement of space electric propulsion. Go ahead, Séverin.
So today I will present you my works on compensation of perturbative effects on the stress measurement MEMS probe for electric propulsion. So the main focus is the electric propulsion. It's rising among the spacecraft propulsion systems. In the electric propulsion, a plasma is formed to produce ions and electrons which are ejected to produce a thrust. So in this system is very efficient. So it enables lighter spacecraft. However, the thrust is very low. So for the qualification of this thruster, we need a specific sensor, specific system to measure the thrust. So actually, the main system to measure this thrust is a pendulum thrust stand, like a simple pendulum where which carries the thruster. For example, here we have the on-air setup that can measure as low as the tenths of micronewton. However, the limits of this pendulum is that they are incompatible with some ground tests, as they are dependent of the vacuum facility, and they are incompatible with some thruster. So the solution is to immerse sensor in the plasma jet, into the plasma jet, like in this image or video. There are diagnostic probe, and we can put in on a thrust sensor to measure directly the thrust. So in the Ionera, previous works show feasibility of this solution, but there are significant measurement bias, because the thruster hits the sensor. There is also ion sputtering, so the ion destroy the sensor, destroys the surface of the sensor, and there are also electrostatic effects like current, unwanted current, or electrostatic force. So in this presentation, the main focus will be to reduce and compensate the thermal effects. So there are global heating of the sensor, but also gradient, temperature gradient into the sensor, which will change the measure. So our first sensor is in fact an accelerometer developed by the Onera. It's an accelerometer. We will use it as a first sensor. So in this sensor, we have a vibrating beam here. And do you see my mouse? So here we have vibrating beam.
Yes, we can. Yeah, go ahead.
We have a vibrating beam, a quartz vibrating beam linked to a proof mass here, and decoupling frame fixed to decoupling frame. So when the proof mass receive a force on acceleration on over one face, it will rotate around two hinges which link the proof mass to the decoupling frame. Thus, the vibrating beam will receive a constraint. We will increase the frequency of the vibrating beam, like a guitar string. When the constraint increase, the vibration, the frequency increase. So the frequency of this vibrating beam is 33 kilohertz. It's thanks to the piezoelectric property of the quartz. And it's proportional to the force. The change in frequency is proportional to the force received by the proof mass. Unfortunately, there are also temperature change, temperature drift, which increase drift in the frequency. So we added a temperature sensor directly into the vibrating beam to measure the temperature and allow compensation of temperature drift. So in this work, we developed several design of this, another design of this sensor with different layer of gold to simulate it, and the goal is to minimize the thermal drift. So by increasing the conductive transfer with gold layer, because currently the reference model is only in quartz, so it has a very low conductive transfer, and the use of the knowledge of the temperature allow to compensate the thermal drift. So we know the sensibility in temperature of the vibrating beam and the temperature, so we can correct the drift. So in this sensor, there are 3 thermal transfers: the thermal load on the proof mass, the radiative transfer, and the conductive transfer. So the thermal load have been experimentally determined as 40 milliwatts per square centimeter. So it's low, but the sensor is very tiny. So it's 1 millimeter long in length. So it can increase largely the temperature. And the main parameter for the radiative transfer is emissivity, which normally we don't know. So we estimated experimentally to be 0.3 for the gold and 0.8 for the quartz. So with the simulation, we apply the thermal load on the proof mass, and we see change in frequency from the initial frequency. So for the reference model, we have 10 hertz, 13 hertz of change, which correspond to 60 micronewton per square centimeter in terms of pressure. So it's very high because we estimated the pressure produced by the thruster is 6 micronewton per square centimeter. So the use of gold layer all over the surface, so in the model 3, and allow to decrease this value to 1 micronewton per square centimeter. So it's a good value, and it allows to do the measure of the force of the pressure of the thruster. So to conclude, in this work, we show that the temperature compensation allow to measure the thrust of the thruster, and it needs the temperature sensor and gold layer to improve conductive transfer. Another thing is that the gold layer evacuates the electric charges of the plasma, so it allows to decrease effects of electrostatic charges on the measure. But I don't have works on it. And to improve the measure, again, we can decrease the thermal load, so increase the distance between the thruster and the sensor, or increase the radiative transfer, so change the gold by another metal with better emissivity. Or the last thing is to increase conductive cooling, which is necessary to change all the design of the sensor. So thanks for your attention.
Thank you very much, Severin, for your presentation. In fact, we are almost back on schedule, and I would like to see if we have any questions from the audience about this presentation. Any questions? So I have a question. It's really a point of clarification, Severin. Where is this sensor placed? And exactly,
so here
to measure the force. Yeah, to measure the force. Where is it placed?
So here we can see the thruster in the actual photo of the dispositive. Around it, there are the thrust pendulum, the thrust pendulum, and this so the thrust is powered on. And in front of the thruster, we have a arm which carry diagnostic probe, and here we can put the thrust sensor.
I see. But in actual application, how is that going to be? So is this supposed to be just for a test setup, for testing, different thrust mechanisms, or is it going to be employed, in the field?
So firstly, it's for qualification. So in the ground
qualification,
test,
okay.
But it could be in the space because, for example, NASA have some experiment with diagnostic probe in front of thruster, but not for thrust, just for other diagnostic probe.
I understand. Okay, there is actually a question from Naga. Go ahead, Naga. The floor is yours.
Thank you. So this sensor also works in vacuum condition or only in air?
So it's only for vacuum, vacuum condition.
Okay, what about in air?
In air, the factor quality of the sensor is very low, so we don't have a good measure.
So this is for
in fact, the thruster.
Sorry, please.
The thruster only works on vacuum condition.
Yeah, to measure in space temperatures. So for the satellite and rocket also we can use this sensor, right?
Right.
Thank you.
Okay, thank you very much. Any more questions? I don't see any more hands raised. So let's thank the speaker again for his presentation. This will bring to a closure our session on sensors. It has been my pleasure and privilege to be the chair of this session. This is the end of the last session of the conference, but it's not the end of the conference. In fact, I'm going to pass this session to Emile for the closing session. So again, thank you very, very much. And Emile, it's now back to you.
Okay, I will start and I will then give the microphone to Emile. So as you said before ending this year event, we need to have a small closing session. And after that, we will also have the breakout rooms for the session you shared previously, maybe, and for also the closing session and the future of DTIP. So this is the 7 times in a row I'm doing this closing session, and it will be the last one. This is the reason why Emile will end this session. So classically, I would like to give you some figures. So some of them have been presented in the introductory session. So as you know, currently there is a very lower submission in all conferences. It was also the case for DTIP this year. We decided to keep DTIP live this year. I hope this will be the last year, and we will recover in terms of sanitary crisis to have a real event last year. The submission of the papers were shared between 12 different countries, with, of course, a big number of papers from France, but with classical countries that are participating. This closing session is, of course, a place to acknowledge all the people that allows us to be here for 3 days. The acknowledgements for this conference for the 4 co-chairs of the conference, Peter, Jérôme, Stewart, and Abdelkrim. Also, all the members of the technical program committee that reviewed the submissions and made the selection of the paper that has been presented for the 3 days. Now some figures about attendees. It was this year a good level of attendance. We are still more than 25-30% attending the closing session, so it's a good result. Overall, we have 99 registered attendees from 22 different countries. And maybe this is the advantage of having a virtual event, is that there is no problems for people to attend. And this year, with the free registration for all students, we have a lot. We had a lot of students registered. So I think it's a good thing for our research domain to have these students attending a conference even if they are virtual. Of course, I would like also to thank the organizing committee and Emile, who will take the lead after my talk, Fred and Corinne Dejoux, that were of great help for me to organize this event. I also already mentioned the conference co-chairs. They have made a good job in selecting the papers and organizing the program. And they will still have a bit of work to do to verify that papers are ready to be published. We also have to acknowledge our communication people and the people that developed the website and also the paper submission website. The steering committee helped me during 7 years to drive the conference, and I would like to thank them all. And finally, it's really important, the seventh person that accept to share a session and handle these difficult conditions in terms of how to give the microphone to the people and share video presentation, live presentation, questions, and so on. Thank you all for sharing your session. And last but not least, I would like to thank our sponsors that allows us to develop this free registration for PhD students. And now this is time for me to say you all, thank you for all these years together. I was very happy to lead DTIP since 2015. And I hope to meet you in the real life for next DTIP that will be organized by Emile Martensik. And Emile, the microphone is yours.
Okay, so next edition of DTIP 2022, to be or not to be virtual, that is the question. I just put that it's a public domain text. I think it's not completely plagiarism, but at the moment we need to be quite optimistic and say that we will have this 2022 session in real life, not in virtual life. And at the moment we are only working on hypotheses, but these are the hypotheses I present to you. We hope that it will be possible to couple this event, this next year DTIP event, with IEEE Samson's France chapter summer school. So this is planned in summer, in July, from 11th to 13th of July. But this is an hypothesis. We need to discuss it with the steering committee and make some decisions. And we have also a targeted place. So this is the Abbaye des Prémontrés. This is in the east of France, near Nancy. So again, nothing is fixed. And I think to get that, we need to speak quite fast because in terms of organization, there's some things to do. And so the right, I think the right thing to do is maybe to wait now for the month of September to pass and then to make the decision, because so we don't know by with this Delta variant and new variants what will happen now, but we know that kids are going to school and normal life is about to come back in France, but also in most of the countries. So we will have some hints on where we can go by this September. So okay. And having that in mind, we will make some decisions and hope to open the submissions for DTIP by the end of January. So this is, for the moment, what I can say. This is a new era for DTIP. I'm very happy to a little bit stressed also to take the chair for next year. And last thing I want to say is to thank Pascal for everything. Pascal said he has been leading DTIP for 7 years, and really it has been a very huge work, very time-consuming and energy-consuming work. And I think we can all thank very much Pascal for all this investment and all this life, because I think DTIP is somehow what DTIP has become and has been is a fruit of the efforts of Pascal's efforts. So I think we can really thank Pascal for all this work. And I don't know how to do that. We have the clapping hands in the.
And we can try to do it in real.
Thank you very much.
Microphones.
Pascal, thank you very much. But it was really a teamwork. So, but thank you, and it was really a pleasure. And we'll attend the next DTIP with a great pleasure.
And so now we can open speakers open the rooms for speakers and for the breakout rooms for any questions to the last session presenters. And also I'll have my own room on room 6. If you have some questions, or if you want to comment things, or make some feedback on this DTIP edition. So
yes, Emile, you're right. I think I will join you in the breakout room number 6. It's really important for all of you. If you have comments, this year we don't set up the participant questionnaire, but we will be happy to have your feeling and to have your comments on this year edition. Even if next year, I'm sure, will be very, very different with a dinner, with a social event, and with a lot of real coffee breaks. So I will open the rooms now.
Just before opening the rooms, yes. I suggest that we could stop sharing the screen for a moment and have activate all our cameras and try to make a group picture of this conference, of DTIP conference.
Okay, I make the screenshot. So it's more than last year. If you remember, Emile was here last year for this photo, and we were less people. So it's a good opportunity to have so many people. So thanks a lot to everybody. Hello, Alexander.
Yeah, thank you, Pascal, for a great job. Thank you very much.
Yeah.
Okay, see you in the breakout rooms for last discussion, and see you next year, of course, for next DTIP.
Yeah. Thank you, Pascal. Bye-bye.
Bye-bye. The rooms are open.